In section 7.2, we're going to look at inverse transforms and also transforms of derivatives. If we go back and kind of analyze what we did in section 7.1, we were given a function that's called f of t. And to f of t, we tried to find its Laplace transform, which we called f of s. So for example, we saw in 7.1 that the Laplace transform of t was equal to 1 over s squared. In 7.2, we're now going to work with the inverse Laplace transform. So whereas f of t, so as we're as L. So remember, what did the Laplace operator do? It gave us a function f of t as its input, and it spit out a function f of s. Well, the inverse Laplace transform is going to start with the function f of s, and it's going to return to us that original function f of t. So whenever we do an inverse Laplace transform, it's always on a function of s, and what we get back is going to be a function of t. Let's call it f of t, little f of t. So as we saw a moment ago, if the Laplace transform of t is equal to 1 over s squared, then the inverse Laplace transform of 1 over s squared would be equal to t. So that's what we're aiming for. We do have a table. Theorem 7.21 gives us the inverse Laplace transforms of some very popular functions of s. For example, the inverse Laplace transform of 1 over s is equal to 1. The inverse Laplace transform of n factorial divided by s to the n plus 1 is equal to t to the n. So in this function, what you're seeing is that the denominator is s to some power. And essentially what we have in the numerator is a constant, where that constant is the factorial of 1 less than whatever you have in the exponent. So for example, if this is like s to the 4th, then you'd want to see 3 factorial up top. If this is s to the 8th, then you would want 7 factorial up top, in which case its Laplace transform would be t to the n. Okay, where n is kind of matching up with the first number of the factorial from the numerator. The inverse Laplace transform of 1 divided by s minus a is e to the at. Be very careful with the next batch. They kind of look a little bit similar in some spots, but one has just a constant up top, and then some have like a s up top. The inverse Laplace transform of k divided by s squared plus k squared is the sine of kt. The inverse Laplace transform of s divided by s squared plus k squared is the cosine of kt. The inverse Laplace transform of k divided by s squared minus k squared is the hyperbolic sine of kt, and the inverse Laplace transform of s divided by s squared minus k squared is the hyperbolic cosine cosh kt. Okay. A lot of times what will happen is you'll be given a function capital F of s that might not necessarily perfectly match up in this form as we see it, but one of the things we can always do algebraically is, multiply and divide by the same constant, and oftentimes you're going to have to do that in order to perfectly fit some of these inverse Laplace transform rules we see in this theorem. Let's go ahead and do a couple examples. Let's take a look at example 1a. Let's find the inverse Laplace transform of 1 over s to the 5th. The rule that this would most commonly look like would be Theorem 7.21 part B, which says the following. The inverse Laplace transform of n factorial divided by s to the n plus 1 is equal to t to the n. But we have a s to the 5th in the denominator. And if we want to perfectly fit this pattern, if we have an s to the 5th in the denominator, then what we would need to have is we would need to have a 4 factorial in the numerator. And we can put a 4 factorial in the numerator if we also put a 4 factorial in the denominator. So it's like multiplying by a form of 1. This part I need to group together because it perfectly suits what we're trying to do in terms of the inverse Laplace transform. And then the inverse Laplace transform is also linear. So we can pull that 1 over 4 factorial to the outside. We get the inverse Laplace transform of 4 factorial over s to the 5th. And that part is simply going to be t to the 4th. So our final answer for this one, 1 over 4 factorial, by the way, is 1 over 24, t to the 4th. So what is the inverse Laplace transform of 1 over s to the 5th? Well, it's 1/24 t to the 4th power. Let's do another one of these. Let's see if we can find the inverse Laplace transform of the following, of 1 divided by s squared plus 7. The rule that this would most closely match up with, if we kind of go back and look through the notes, would be Theorem 7.21 part D, which says the following: the inverse Laplace transform of, so first of all we have the sum of 2 squares in the denominator. You need whatever's being squared at the bottom to be up top. And if that's the case, then this is going to be equal to the sine of kt. So we look at it and we say, okay, let's try to rewrite it so it fits this perfectly. So we have a 1 divided by, we want there to be a sum of squares in the denominator. And one of the ways that we can do that is we can write 7 as the square root of 7 squared. And so now we see the thing that's playing the role of k over here is that number square root of 7. But we also need a k in the numerator to get this to work. So we're going to do the same trick. Let's multiply the numerator by the square root of 7 by also multiplying by a 1 over the square root of 7. Okay. If we do that, then this one, again, we can pull to the outside. We have 1 over the square root of 7, the inverse Laplace transform of the square root of 7 divided by s squared plus the square root of 7 squared, which is going to be 1 over the square root of 7 times the sine of kt. Remember, k is the square root of 7. This is the square root of 7t. So that's what we get for part B. Much like we saw with the Laplace transform, the inverse Laplace transform is linear as well. Okay. Meaning that if we have the inverse Laplace transform of a, maybe I'll be consistent here, let's call it C1. Now remember, these are functions of s. So C1 capital F of s plus C2 capital G of s, then this would be equal to C1 times the inverse Laplace transform of F of s plus C2 times the inverse Laplace transform of G of s. With that in mind, let's try and take a look at example 2. Let's find the inverse Laplace transform of negative 2s plus 6 all divided by s squared plus 4. what we can actually do is we can split apart the numerator. We're allowed to do that. And this would become the following. It's going to be the inverse Laplace transform of negative 2s over s squared plus 4 plus the inverse Laplace transform of 6 divided by s squared plus 4. Because inside, right, you can split apart the numerator. So write the inside like this. Then via the linearity of the inverse Laplace transform, we get that. And now if we want to, and we should, we can pull those constants out. So we're looking for the inverse Laplace transform of s divided by s squared plus 4 plus, pull the 6 out, we have the inverse Laplace transform of 1 over s squared plus 4. And in order to take it from here, we want to use the following common Laplace inverse transform theorems. The inverse Laplace transform of s divided by s squared plus k squared, that's equal to the cosine of kt. And then for the one that we have over here, we're going to utilize that the inverse Laplace transform of k over s squared plus k squared, that inverse Laplace transform is equal to the sine of kt. So let's go ahead and write this out. So essentially what we have right here is that this thing here, this is immediately going to be the cosine of t. So we have negative 2, excuse me, not cosine t, cosine of 2t, because our k is 2. Actually, no, sorry, excuse me. Yeah, that's right. That's just cosine t. That's right. And then, because this k here, right, is 4 squared, which would be 2 squared. So k is 2. And then over here, we have to kind of fit it to the form. We have a k, which would be 2 squared, but we would also need a k in the numerator. So we can multiply up top by 2 if we also divide on the outside by 2 as well. So this is going to be plus 6 divided by 2 is 3. And then with that extra factor of 2 on the inside, now this would perfectly become the sine of 2t. So our Laplace transform for this one, we get negative 2 cosine 2t plus 3 sine 2t.